Okay, so everything on here has been a problem on an exam at one time or another. I think I actually found 2 exams and pulled some from one and some from another. Sometimes my exams hit at different time periods. So anyway, all of these have been on there, except for number 6. I won't ask sample size problems on this exam, so we'll skip that one when we get to it. We did cover that Friday, but I think we'll stop with the true proportion z-test. So anyway, the first thing in any of these is to determine what kind of problem, and then just to write down the information from the problem. As soon as you see sample standard deviation, that means you're going to have a t-test for one mean. Could be for 2, but there's only one sample here, so one sample t-test on this one. And then I'm just going to write down the information from the problem. We have a sample size of 36. We have a sample mean of 143 and a sample standard deviation of 12.6. And we want to know if the population mean is less than 150. And so HO will be equal to 150. Always have an equal sign in the null hypothesis. And some form of inequality, in this case, less than in the alternative. R is research, same thing there. You could put that in here. See if it comes back. Well, no. Well, hopefully you got that down. Just work it now. Okay, so again, I'm just going to rewrite a little bit of this. Again. HO was mu equal to 150. HA was mu less than 150. So using the critical value approach, we're going to reject HO if t-test is less than minus some value. So whenever the alternative or research hypothesis is less than, this is going to be less than minus. We had n is equal to 36. So that means the degrees of freedom is 35. That's just n minus 1 when you have a one sample t-test. And this is a one-tailed test. Alpha was 0.05 on that. So just go in that case, one-tailed test, 0.5 down to 34, and that's 1.691. So your t-test is equal to the statistic, which is x bar, minus the hypothesized mean, over S x bar. What was the sample standard deviation in this? 12.6. And so if that's the standard deviation, just S, or if you want to put standard deviation of the x's. But what we need is the standard error of the x bars, which is S divided by the square root of n, or 12.6 divided by the square root of 36. And I believe that'll be 2.1. So we have 143, that was the sample mean, minus the hypothesized mean divided by the standard error. Get that to be minus 3.33. And minus 3.33 is less than minus 1.691. Therefore, we reject HO. Conclude that mu is less than 150. Which means the average sales, we're confident that average sales is less than 150, that this 143 can't be accounted for by chance alone. There's some real effect there. And all of these, we're really trying to distinguish between, when we say mu is equal to 150, it doesn't have to be equal to 150. We're just saying it could be true. When we get to our research hypothesis or alternative hypothesis, we can reject HO. We'll show that whatever difference we observe, in this case a difference of 7, is unlikely to have been due to chance. I highly recommend that you use your calculator to go ahead and check these. Plus, in any of the problems with the t-test, we're going to use our calculators to obtain the p-value. So I'm going to just do stat, tests, t-test, mu0 is 150. Make sure you're entering stats, not data. X bar is 143. Make sure you enter the standard deviation for the x's, not the x bars. So enter the 12.6 for the standard deviation of the x's. The sample size was 36. We had less than. We calculate that, and first of all, you can see that our calculation of the t-test was correct. But that you can also see that the p-value is 0.001. Kind of afraid to hit pause right now and think I'll lose it. Does anybody have any questions to this point? Now let me go back to regular cursor. That's not good. Maybe I can do it with this. This is a new one. Okay. And a new way to get around this thing. Okay, so now for the p-value and drawing the sampling distribution. Make sure you label the axis with whatever the statistic is in the problem. X bar in this one could be p hat, x bar a minus x bar b, p hat a minus p hat b. Any of those, and this one is a problem of x bars. The center of the distribution is equal to whatever you have in your hypothesis, in the null hypothesis, which was 150. Then along the axis, This would be the specific value of the statistic we observed in this problem, which is a sample mean of 143. And then in the direction of your hypothesis, which we had less than, this then is your p-value of 0.001. So two things here. We would reject HO if the p-value is less than 0.05. That's always less than. That doesn't change. P is probability value. We'll always reject when the p-value is low. So 0.001 is less than 0.05, and so the reject HO. Same conclusion we had above. I'll also ask you to write an if-then statement, or I might say write a conditional statement that explains what this is. Basically, all you're doing here is writing this picture, taking this picture and putting it into words. If HO is true, then there is a p-value chance of getting the area that we have shaded. Okay. So if mu is equal to 150, then there is a 0.001 chance, it's about, 1/10 of 1% chance that, I'll be a little bit more, I'll just put this, that we would obtain a sample mean less than or equal to 143. Most people don't do it, but to be exactly precise, that is, and you really don't have to write this in there, but I want to be precise here. That's with sample size equal to 36. If the sample size were something else, then the distribution would be narrower or wider depending on the size of the sample. If it were a larger sample, it would be narrower, smaller sample, wider. So it really is tied to that sample size. You must have the if statement in there. You can't just say there's a 0.001 chance, because if this weren't true, let's say that the population mean were 143. If the population was 143, just to get in there, if this were true, then what's the chance you get less than 143? 0.5, 50%. So, the chance of less than 143 depends on where the population mean is. Population mean were 149, you wouldn't have this exact probability. So this p-value probability is conditioned or conditional on having this hypothesized mean. I think the other problem that was asked in this problem was, is the sample size large enough? N is 36. And in the problems involving means, remember this is different with proportions, but in problems dealing with means, you have to look at that 15, 40, 100 rule. So 15 is skew. We're greater than or equal to 15. Skew's okay. We are not greater than or equal to 40. That means that this process, or this whole process that we've done, the probability for the p-value, the critical value, we did a confidence interval. If there were outliers in the population or extreme values, then this process, at worst, or at best, is inexact. Worst, just not good at all. Especially if you had extreme values that could really bias or throw off your results. questions on this? And this one I would say it's large enough as long as there are no outliers or extreme values. You could even go on to say skew would be okay, but outliers or extreme values would invalidate the inferences that we have. Other questions before this gets erased? Okay, and problem 2, we have 100 business students. Sample mean was 6.3, sample standard deviation 1.2. As soon as you see sample standard deviation, you know we're dealing with a t distribution. But now we have another random sample of 100 students. That means we have a t-test for 2 samples, or the 2-sample t-test. And of course here we have a sample mean of 6.8 and a sample standard deviation of 1.8. Is there a difference between the 2 population means? So HO is mu A equal to mu B, and HA is mu A not equal to mu B. And let's go ahead and write down the information from the problem here. Group A, Group B, N, X bar, and S. So we had 100, 6.3, 1.2, 100, 6.8, and 1.8. So that's just writing down the information from the problem. When you do the 2-sample t-test, the first thing you need to know is, should we pool or not? Should we pool the variances? If they're close together, variances are close together, then we'll pool them together as if we just have one variance. That actually gives us a slightly better estimate, but more importantly, it changes the degrees of freedom when you look up things in the t-table. So I'll have to square these. That's 1.44 and 3.24, and 3.24 is more than 2 times as great as 1.44. Therefore, they're not close enough, and so we'll use the unpooled test. Now, this says to use your calculator for everything. I'll write the formula anyway in a minute, but if I give you a problem, and there will be at least 1 or 2 problems on this test, and almost all, if not all, the problems on the final exam, you'll be able to use your calculator. So before we do that, we will need to say reject HO. If t-test is greater than some value or less than minus, we'll have to get our degrees of freedom from the calculator. And this is the one when we had the unpooled, it's going to come out to be a decimal. There's really a huge formula, which I'll be glad to supply for you if you can buy. I've worked it, I think, maybe 2 or 3 times, other than that. So stat, test, 2 sample t-test, just plug in the information from the problem, 6.3, 1.2, and 100 for the first one, 6.8, 1.8, 100 for the next. Make sure you select not equal to the 2-tailed test. And no for the pool. We're not going to pool. One variance is more than twice the other. There's actually a separate hypothesis that tells you whether or not you can assume equal variance. We won't do that in this class. You might see it on some computer output, but degrees of freedom, 172.5. So that means our table only goes to 100. And if you look at the table, if you go down each column, what you'll see is the numbers get closer and closer to whatever the z-value is. So once we get over 100, we'll just use whatever the z-value was. And for 0.05 in a 2-tailed test, that's 1.96. Really, it's probably a little slightly lower than that, but you can see by the time we get to the bottom with degrees of freedom of 100, we're already down to 1.98. So we're not going to be that far on. While we have the output there, you can see that the t-test is equal to minus 2.31, which is less than 1.96, less than minus 1.96. Therefore, we're going to reject HO and conclude there is a difference between the two means, that in terms of should be put this back into the words of the problem, that looks like there's a difference between business and computer science students. On the scores for the case. I can actually tell you those scores were actually, this actually is a case that I've had students analyze. I made up these results just for the sake of a problem that the score was based on, was an ethics kind of thing, it's an ethics case. So it looked like in this case, business students were less ethical. That may not be true, I just made this up. At least the results. Question on what's up there? Right, this is a 2-tailed test. So 2-tailed test, 05. We'll just have to go down to the bottom because we don't have 172. We'll just go down to the bottom. Not asked for on this one, but I'm going to go ahead and write it down anyway, that the standard error of the x bar A minus x bar B, all that x bar A minus x bar means is that's your statistic, is equal to the square root of s squared A over NA plus s squared B over NB. And that if we were going to compute this t-test, it would have been x bar A minus x bar B, t-test is equal minus mu A minus mu B hypothesized statistic minus hypothesized parameter divided by x bar B divided by this whatever we had there for the standard error. And also that for tests of difference between two means, this will also be true for the matched pairs t-test and also true for the difference between proportions. This hypothesized parameter is going to be 0. So for 3 out of the 5 or 6 kinds of tests you can have on this test, half of them, the hypothesis will be 0. And see, we could have on this HO, mu A minus mu B is equal to 0. That is the null hypothesis. If they're equal, then the difference is 0. I know I'm kind of off on to just other things now. Everything I have in green here is not part of the problem as it is. But if we were doing the p-value on this, the center of this is going to be 0. That's mu A minus mu B is equal to 0. That's the center. What we're going to have over here, let's say this is x bar A minus x bar B is what you have over here. What number are we going to have right here? It's going to be minus 0.5. That is 6 minus 3. It's x bar A minus x bar B. 6.3 minus 6.8. So x bar A minus x bar B is just 6.3 minus 6.5 or minus 0.5. So minus 0.5. This curve is, this distribution, this sampling distribution, is the difference of the differences between x bar A, x bar A and x bar B. So it's the minus 0.5. Be also careful on this one. It's a two-tailed test. So you also have p-value on the upper end, and this value is 0.5. So I'm going to write this up at the top here, just the conditional statement. If mu A is equal to mu B, you could also put if mu A minus mu B is equal to 0. Then there is a p-value chance, which is 0.022. Just reading that off my calculator. Or 2.2% chance that one of the following is true. X bar A minus X bar B is less than minus 0.5. That takes care of this part of the p-value. Or X bar A minus X bar B greater than 0.5. That's this part over here. So on a two-tailed test, make sure you get the p-value in both tails. And if you used your calculator, it gave you the total p-value. As long as I selected not equal to, that 0.022 has already added up both of these. Remember on the ones when you calculated the z-test, you're calculating and computing and looking up getting one tail, you have to double that. So when you're using the z-test and calculating by hand, of course, again, you should check that on your calculator. And you have .011, but on your calculator you got .022. You forgot to double. That wouldn't be relevant on this one, but on the z-test problem, it would be. Other questions on this one?
Before I start recording.
The first thing you should do, let me go, this is what it's going to say down here, use your calculator. But it's after and before. Each row here is just one person. That's a matched pairs t-test. So if you would, if you have your calculator, just go ahead and enter the numbers that are there into lists 1 and 2. Understand, if you try to work this one by hand, your chances of finishing the exam will diminish considerably. If you try to work this as a 2-sample t-test instead of a matched pairs, you probably don't have much of a chance of finishing at all. Okay, so again, in this problem, we have after and before, and each row is just one person. So really what we're going to do is focus on the improvement that each person made. Or in this case, this is pretty cool. Just looking through this, what would you, okay, all right, maybe not. We're looking at how much the job commitment went up after this program. So Allie increased by 2, Beth by 18. That's just how much they improved. Now, on the exam, since I said you can use your calculator, you don't have to do all of that. There may be a problem where you do, and if you did, be prepared to compute the standard deviation, the mean and standard deviation of these numbers. But what I want to get at here is with the matched pairs, once you have these differences, then these numbers are all irrelevant for the problem. This is just a 1-sample t-test for the improvements. So don't treat this as once you've done this, and once this and stated the hypothesis, it's just exactly what we did on, I think, the first problem, the one sample t-test. So the hypothesis before and after, we want to know if it's higher before the mean greater than 0, because I subtracted after minus before. If you had done before minus after, you're saying it's lower before, then everything would be reversed to what I'm going to do. This one makes more sense to me in this case anyway, and that's equal to 0. It's just one mean. You will find books that say mu A minus mu B on this. In my opinion, that's just really the wrong way to state it. It's one mean. It's the mean of these numbers, the differences. Its critical value approach, degrees of freedom is 9. There are 10 of these numbers. There are 10 employees. So we're going to reject HO if t-test is greater than some value. And it looks like I didn't put an alpha on this, so let's just say that the level of significance is 0.05. So we'll go down to 9 degrees of freedom there, and that's 1.833. So do this over here. I had my after scores and my before scores, and I had these in list 1 on my calculator, and then these in list 2 on my calculator. Go to the top of the column that's labeled L3 and highlight the L3. If you highlight the list number, then you can write a formula to calculate all the numbers that would go here. So you'll just do second 1, which is L1, minus second 2, which is L2, and then L3 will fill in with the numbers 2, 18, 4, minus 6, 5, and so on. Is what you should have in your calculator. And then to calculate the t-test value, we're going to select stat, tests, t-test, which is option 2 on your calculator. And at the top, where it says input, make sure that you have data selected, because we're putting in the actual data. We don't have a problem where we've already computed the mean and the standard deviation. So highlight data. Your mu0 will be 0. That's from right here. And then where it says list, refer to list 3, because that's where these numbers are at. The 2, 18, and so are now in list 3. Don't change the frequency thing. Make sure your hypothesis is greater than, and then calculate. And I get a t-value of 0.47. So t-test is equal to 0.47, which is not greater than 1.833. So we fail to reject HO. We conclude that the training might not improve commitment. If you've ever worked somewhere and had training, you would be surprised if it didn't lower commitment after you come to the wasted training period. But anyway, I made something where at least went up some. Now, we're not going to say that it doesn't increase. We're just saying it might not, because our sample mean, if you look on your calculator, that's calculated too. The sample mean was 1.3. So in the sample, it did go up. It's just that could have been due to just natural variation in the data. if you look at your p-value, it's 0.32. There's about a 32% chance you would get a sample mean of 1.3, even if there were no difference. So when you fail to reject HO, some equivocality might or could be is appropriate. Without calculating, and this isn't part of the problem right now, but without calculating, what can you tell me about the confidence interval? Let me put it this way. Does the confidence interval include 0? It does. We fail to reject HO. They might be the same. There may be no difference, and that's 0. If you fail to reject HO, then the confidence interval is going to be 0. In fact, we can check that right now. Now, just go stat to test. You go down to T interval. And let's say we were doing a 90% interval. And calculate, and you can see that it's going to go from minus 3.7 to positive 6.33. We're saying, when we fail to reject HO, we're saying this could be true. It could equal 0, which means the interval will include that. Of course, your recommendation would be do something. If you're trying to raise job commitment, this may not be the way. I wouldn't spend a bunch of money on this program. I wouldn't spend any money on it if it's not going to do what you intended for it to do, unless there's some other outcome, maybe it increases productivity or something. But if this is all we have and this is what we're interested in, then you should find some other way. Save your money. Questions on this one? Probably, in terms of points, the most frequently, the big point loss on this test in the past has been in distinguishing between a matched pairs t-test and a two-sample t-test. Because I could have given the same exact data, and instead of saying after or before, that could have been, let's say, the gas mileage for car A and car B. It could have been the performance for a group of people that were trained and another group of people that weren't trained. Now, if that were the case, that first row, that 79 and that 77, one of them might be Allie, and the other one would be Al, or Alan, somebody different, so different people. So what makes this a matched pair test is that each row here is one person. But again, if this person is Mel and this one is Jack, those are two separate groups. And it would be an independent samples t-test. And if that were the case, then these numbers are the numbers that you would pay attention to. And if you were doing things by hand, you would compute the mean and the standard deviation of group A, let's call it. And then you would compute the mean and the standard deviation of group B. Check to see if you had pooled variances. Then do a t-test for either pooled or unpooled. One group, there are only 10 people here. They're their names. Two separate groups is a two-sample t-test. Your question from this one? Yeah. Okay, so in this problem, first of all, I'm going to look and see population standard deviation. population standard deviation is sigma. That means we're doing a z-test. Sample standard deviation, t. Population standard deviation, z. And let's see, that's 7.5. We have a sample mean of 39.2. And we have a sample size of 30. And we want to know if it's not equal to 40. So mu r is, or mu a, however you want to call it, is not equal to 40. So that means, remember now, if this is a two-tailed test, I'm going to go ahead and just put the idea in here. We're doing a p-value. That we're going to have p-value in both tails. Write down the information here. X bar is equal to 39.2. Sigma is equal to 7.5. And n was equal to 30. So this is 40. I'm actually, I might come back and do this or post it. We've been doing enough of the critical value approaches. I want to try and get as far in this test as I can. So we haven't done as much p-value. Let's do that. But what I want to get at, as soon as you see that not equal to, you know that's going to be two-tailed. Here's your 39.2. So there's some of the p-value. But there's more over here. And this distance is 0.8. So we need the same distance above the mean. So that's going to be 40.8. I'm going to compute the critical value. Z-test is going to equal X bar minus the hypothesized mean over the standard error, sigma X bar, where sigma X bar is equal to population standard deviation divided by the square root of n, which is 7.5 divided by the square root of 30. Or 1.37. So we're going to have 39.2 minus 40 over 1.37. And that's equal to 0.58. I can just go ahead and tell you on the critical value approach, you would have rejected if it's greater than 1.96 or less than minus. And that's not, you would fail to reject HO. But for the p-value approach, we know that from here to here is 0.58 standard deviations. So we'll go to our z-table to 0.58, and that's 2190. That's here. So the area out here is 0.5 minus 0.2190. That's 2810. So 0.2810. But remember with the two-tail test that there's another 2810 over here. So the total p-value is equal to 2 times 0.2810 or 0.5620. think before I go any further, I'm going to put this into my calculator just to make sure I didn't make any arithmetic errors. I'm going to go to Stat, Test, Z-Test. Stats, I'm entering statistics. Mu0 was 40. Population standard deviation was 7.5. The sample mean was 39.2. The sample size was 30. We have a two-tailed test, so just select not equal to and calculate. I get minus, p-value is 0.56. Pretty close. There's going to be some rounding because their z-value is minus 0.584. Well, they can calculate. We're just using a table. So the p-value is 0.5620. So interpret the p-value two ways. I'll be more explicit about this on the test. One is just test the hypothesis. The other one is the conditional statement. So just to test the hypothesis, we're going to reject HO if the p-value is less than 0.05, 0.5620 is not less than 0.05. So we fail to reject HO. And conclude that the population mean is not equal to 40 and that you're not filling the bottles correctly. Which implication would be you need to reset the machine. And that's why this is a two-tailed test. Before you collect any data, you're interested in whether there's too much or too little. So the decision here is, should we shut down and adjust the machine so it's putting in the correct amount of, or getting the right, in this case, I guess, mean content, it's not a fill. We don't have the right caffeine content. We're testing this out. It could be either too high or too low. If it's not in the right range, then we're going to shut things down and readjust the machine so we have the right caffeine content. So now that conditional statement. If mu is equal to 40, if HO is true, then there is a 0.5620 chance that you would either get X, one of these is true, X bar less than 39.2 or X bar greater, you could put less than or greater than is making this greater than equal to 40.8. It has the confidence interval on there. We'll compute that in a minute. One thing we do know, since we failed to reject HO, this could be true. We know that the confidence interval is going to include 40, because that could be true. There's also the question here of sample size. Our N is 30. So skew would be okay. This process is valid if there are skew. It's not okay. There are outliers or extreme patterns. If there are, then you should have a larger sample. Questions on this? Before I race? Okay, so for that confidence interval on this one, we're going to have X bar, the statistic, plus or minus a confidence coefficient, which is going to be z, because we had a population standard deviation, square root, let's just put sigma x bar. If you put x bar plus or minus z times sigma divided by the square root of n, that'd be okay. But let's say we've already computed that. So we have 39.2 plus or minus, and with 95 here, we would have 1.96. And let's see, I'm doing this from memory. Was that 1.37 for the standard error? I think it was. Is that what we have? Okay. So then we can calculate from there. 39.2 minus 1.96 times 1.37. And if you put that in your calculator, you would now hit second enter. You can just go change that minus sign to a plus. And I have 36.51 to 41.89. That interval includes 40. Okay, I've only had one cup of coffee. On the past one, did I say you should shut the machine down? And we failed to reject HO, it could be 40. I should have said no, it's within the range of 40. I can't remember what I said now, but if I said shut it down, then I should. But anyway, it includes 40. So that's what we expect. That's what we want to have with the 40. Therefore, you just leave things alone and go on. That sort of brings up another kind of issue. I'll put it in a different context. When you guys are seniors, in your last class, your business policy class, you're going to take an exam. It's called the ETS Major Field Test. And it basically comes to, if you're a business major anyway, and it's going to test you across different fields, accounting, economics, management, marketing, so on. It's going to have questions on there. You're going to get a score. And let's say that it's out of 200 points, that last time when we took this, to actually get a percentile thing, let's just say that last time we were in the 72nd percentile. Now let's say we get some new information. And this time, we're in the 49th percentile. Are things, what should we do? Should we let's revamp our whole program? The answer is, I can remember when a friend of mine actually was the dean and I was the department, and they came down with this and he was all upset. I said, Tom, go take an answer. Because things are going to change from time to time. There is sampling error. And if you go back and, for one thing, this could be on sample size. In fact, this happened a lot. We tend to have more people graduate in the spring. This happened to be a fall test. We maybe had 23 students take the test. It could be that we just happen to get a group of 23 students up. Let's say maybe they weren't the brightest group that ever came through. And the next time we take the test, maybe it's going to be back to 78 or 72 or more. So the reason I say that is, we're looking at this 39.2 here. The question really comes down to, at what point? You see, we're not just talking about this mean, we're talking about this natural spread in the data. And so what I'm saying here and what I'm saying here is there's going to be some variation around. You're not going to always get 40. Let's say that over a period of time, our real average was 63. Well, sometimes we're going to get above that, sometimes below. And if you have small sample sizes and a lot of variability, then you're going to expect more change. What you really ought to look at, this is a different problem altogether, what you really ought to look at is, I always told them, you ought to be looking at a 3-semester rolling average and then just update that. Or actually, probably 4 would be better since you have 2 falls and 2 springs in there. This also, it's not as big of a deal now as it was a few years ago. They used to be talking about consolidating schools in this day. And they would have these really small schools. Maybe the high school would have, let's say, 22 or 23 graduates a year. Well, one year, they would get this score that puts them way low in the average for the state. So everybody's talking about shutting down. Let's say, look, we take it to an extreme. Maybe they only have 12 graduating schools. And we have schools that do that. Awesome. I haven't had my microphone on. So, oh well. I'm glad you're here. You get to see the whole thing here. That's awesome. I had it on and I went up to get some more exams for you guys. But, oh well, maybe they can hear it. It's moving. Maybe that microphone's really good. They once told me, some students in my class, it is going. Pretty good microphone. Sometimes I mutter under my breath, like if I make a mistake or something, and I try not to curse really bad. But, you know, my students indicate that they could hear under my breath some of the things that I said. I asked them if I should erase it, and they said no, that it made me seem more human to every once in a while have that. Yes. 17 in your grade. So 1 year, the scores are low. And maybe you just happen to have 4 or 5 students or whatever that, I don't know, they're just not the brightest bunch that's come through. And so the score is low. And the next year, you have 3 students that are just genius. Now your school looks like it's the best school in the world. The scores are way above the average. And the smaller your sample size is, the more you should expect that kind of fluctuation. Now, if you were, I don't want to call your town Podunk or anything, but okay, I guess I am. Let's say you're from Podunk, whatever, and you've got that wild variation. You shouldn't expect, would you expect the same amount of variation out of, let's say, Bentonville High School? Just the largest school in the state in terms of number of students? No, you're not going to get as much variation there because they have a huge sample size. And they're always going to get some people on either end of the thing. So having a couple of really bright people or a couple of really not so bright people isn't going to have an impact on you when you have, I don't know how many students they have. Do you guys, a couple thousand or so? My granddaughter graduated from there, and they had to go get Barnhill Arena to graduate, and it was full. As full as a Razorback game, except for I don't think they used, was it in Barnhill? No, it wasn't in Barnhill, it was in the new, whatever it is, Bud Walton thing. That thing was full. They have a lot of students, but they're not going to have the variation that you would with a small sample size. So anyway, my whole point on that is that we're trying to determine when we ought to pay attention. And should we pay attention at 39.2? Our answer in this case is no. It's within the normal range of variation that we would expect. Okay, so number 5. And this one we have 25 bookstores in the South, 18 sell coffee, 25 in the West, 23 sell coffee. First of all, there are no means, there are no standard deviations. First clue, if we're talking about proportions. They either sell coffee or they don't. That's just way back from the very beginning, a binomial kind of thing. They either sell it or they don't. So we're going to talk about the proportion that sell in each one. And then, of course, the final clue is there a difference between the two population proportions? When all else fails, read the problem. Okay? So, is the sample size large enough in this problem? And the answer to that is no, it is not. Because with proportions, all the yeses and nos had to be greater than 10. If you listen to some of my videos, I said 5. Up until a few years ago, all the books said 5. And in the last, I don't know, some books have changed and some not, but or at least the rate of change. I'm going to say in the last 3 or 4 years, almost all the books are saying 10 now. So anyway, some of my tapes are going to say 5. Let's go with 10. But in the South, we had 18 yes and 7 no. 7's not bigger than 10, so not big enough. In the West, we had 23 yes and 2 no. By any standard, 2 no's makes this a not large enough sample. There are times when a sample size of 10,000 is not large enough. I'm not sure if we've read this section in yet. We will. In the How to Lie with Statistics book, they're talking about tests done on the polio vaccine, and they had samples of maybe 5,000 or 6,000, but it wasn't large enough because in 5,000 or 6,000 people, on average, there were maybe 2 cases of polio. So in order to make any comparison, you had to, in that case, have a very large sample, maybe 100,000s or something like that. They actually had more than that when they did those tests, I think in the 50s, maybe early. Well, I think in the 50s. Salk was the guy's name. But anyway, so we're going to go ahead and work this, but everything that we do is not valid in this. I'm just going to work it to show you how to do it. It would be appropriate if you have the guts on a test to say, I'm not going to do part B and C because the sample sizes are not large enough for this process. Take a little guts, but you could try it. This problem showed up. It probably won't, but apparently it did one time. And actually it's happened a couple of times over the years. And I actually have had people have enough guts to say, well, we shouldn't do that because the sample size is too small. I gave them bonus points for having done that. The safe might be to say, no, it's large enough. I shouldn't do the rest of this stuff. But just in case, I'm going to show my work anyway, so I don't just make 0 points or anything. But anyway, I think it says use the calculator on this, but this is the last thing we covered, and I think probably it would be better at this point for me to just go ahead and work this one out all the way. For the confidence interval, let me reorganize what I have up here. And say that what I have is group A, put that over here, group A and group B, and that in the first group, X, the number of yeses was 18, and that's out of 25.
And in the second group, that was 23 out of 25. So P hat A is going to be 18 out of 25. That's 0.72, just 18 divided by 25. And for P hat B, it's going to be 23 out of 25, and that's going to be 0.92. Actually, I'm going to really do a couple of things different on this problem just to make sure we have everything out there. In this case, for the confidence interval, I'm going to have P hat A minus P hat B plus or minus the square root of P hat A, Q hat A over NA plus P hat B, Q hat B over NB. And I'm going to do one other thing here. This designation of A and B is arbitrary, and to me it's easier to think of a difference of 0.2 than it is a difference of minus 0.2 when I do this interval. So I am now changing this to be group A and this to be group A. It doesn't make any difference which order they're in. It's just two different groups. But I like having the bigger one first. So I'm going to call that B and that A. So I have 0.92 minus 0.72 plus or minus the square root of 0.92, 1 minus that, 0.08 over n of 25, plus for B, 0.72, 1 minus that is 0.28 over n. Sorry about that. This is a, let's make this 95%. There should be a Z right there, confidence coefficient, and there's going to be a 1.96 in there. 2 minus 1.96, or 0.2 minus 1.96 times the square root and this one's going to be close. I'll check my stuff on my calculator in a minute, but I'm getting minus 0.006 to 0.406. I'm putting that in my calculator. Stat tests. I'm going to go down to option B, 2 proportion Z interval. And I'm just going to put 23 out of 25, 18 out of 25, and 95, and calculate, and I get exactly the same thing, so I'm feeling pretty good about my calculation now. Minus 0.0056 is what I rounded to 0.006. So that is part B. Based on that, can you conclude there's a difference? And the answer is no. The interval includes 0. Barely, but it still does. 0 is in the interval, so we can't conclude there's a difference. No, 0 is in the confidence interval, the 95% confidence interval. Questions about that part? I'm actually going to stay with this problem a little bit longer. I'm going to I'm going to add a hypothesis test to this. Two proportions the interval. It's option B on your calculator. And then all you have to do is enter those numbers and the confidence level. It'll have XN, XN, and then the confidence level. And the proportion ones are quite nice on your calculator. You just put XN for the one and then your, in this case, confidence level. But it's option B on your calculator, stat test. Make sure on the confidence intervals that you go down to the intervals. As I've said before, if I had been in charge of designing this menu, I would have put Z-test, Z-interval, T-test, T-interval, and gone down that way. But they put all the hypothesis tests followed by all of the intervals until they get down to the bottom, and then there's some different things. Other questions on this? Let's say now that this were a hypothesis test and we're going to do the critical value approach. And the reason I want to do that is I want to make sure you understand that for both the 1 and the 2 proportion tests, the formulas for standard error differ. Okay? This will not be the standard error that we use for hypothesis testing. It's going to be slightly different. So let's say this was, we still want to know if there's a difference, but we're going to, instead of a confidence interval, we're going to use the critical value approach, and alpha is 0.05. So putting this in the order that I had there, 23 out of 25 and 18 out of 25. We already had P hat A was equal to 0.92 and P hat B is equal to 0.72. If HO is true, let's go ahead and put that. HO is going to be PA equal to PB. Or if you prefer, PA minus PB is equal to 0. HR will be PA not equal to PB. Make sure you get the symbols correct too. It's always parameters in the hypotheses, P's and mu's, not X bars and P hats. So all the hypotheses are population parameters. But anyway, when we do this test, for purposes of doing the test, doing the critical value, calculating the p-value, we're assuming that's true. If that is true, if they are equal, then you shouldn't be thinking about two separate groups, A and B. If they're the same, then they're just the same. It's just one larger sample. So we're going to pool those, and we're going to say that we have a total of what would that be? 41. That's just 23 plus 18. We had a total number of 41 stores that sold the coffee. These 18 and these 23. And we have a total sample size of 50. These 25 and these 25. And that means that for the whole group, which we'll call P bar or pooled P, it's going to be 41 out of 50 or 0.82. if the sample sizes are equal as they are here, that's just the average of the 9.2 and the 7.2. If those sample sizes aren't equal, then it won't be a simple average. It's a weighted average, and this is probably the easiest way to do it. Just get the total number of yeses, the total sample size, and get that proportion. So for critical value, we would reject HO if z-test is greater than 1.96 or less than minus 1.96. And our z-test is going to equal the statistic p hat A minus p hat B minus the hypothesized proportion PA minus PB hypothesized over the standard error, which is the square root of P bar Q bar 1 over NA plus 1 over NB. Moving that over here would be on the top 0.92 minus 0.72. That's P hat A minus P hat B minus 0. That's the hypothesized difference between the population proportions divided by the square root of 0.82, this pooled P, 1 minus that, which is 0.18, times 1 over 25 plus 1 over 25. And I'm going to cheat here. Instead of putting all that in my thing, I'm just going to go to the two proportion z-test on my calculator. I already have the 23, 25, 18, and 25 not equal to and calculate. So that should come out to be 1.84. It might be, if you really calculate out by hand, slightly different than that, but that'd just be rounding. 1.84, that's, let me write this up here. 1.84, that's my z-test. That's not greater than 1.96. That's not less than minus 1.96. So we'll fail to reject HO. This could be true. The population proportions could be the same, despite whatever preconceptions you might have about bookstores and coffee in the South and the West. I don't know, I guess we're all drinking coffee now. I remember driving around Oregon 20 years ago, and there were coffee shops everywhere. But I guess they're here now too, you know, like Starbucks and all of that stuff, where you can go and pay $5 or $6 for a cup of coffee if you like. I've been there, you know, a few times, maybe 10, something like that. Questions on this one? Not going to do it right now, but remember in this one, if you did do a p-value, calculate it with a z-test, you'd have to double the area in the tails because it's a two-tailed test. You have not equal to in the hypothesis there. Okay, we're running out of time today. Not going to have number 6 on this one, the sample sizes. I'm just going to quickly just say what kind of problem, and then, well, it looks like, okay, number 7. And this one, we have 500 car crashes, 261 within there, and we want to know if more than 50%, which is the same thing as saying the population proportion greater than 0.5. So HR or HA is going to be P greater than 0.5. So this is going to be a one proportion z-test. And again, just quickly here, if it doesn't ask for one, but yeah, it does. Here's a confidence interval. When we get to the confidence interval, it's going to be P hat plus or minus z times the square root of P hat Q hat over n. And that P hat is 261 out of 500. That's going to be what, 0.522, I think? Let's say I got that right. Z for 90% is going to be 1.645. And this is going to be, I have to write it down here, 0.522. 0.478 divided by 500. So we're using the sample proportion there. Remember, with the confidence interval, there doesn't have to be a hypothesis. What I really want to get at is when we do the hypothesis test, that, and of course that'll affect the p-value too, 0.05, we're going to reject HO if z-test is greater than 1.645 and the z-test is going to equal the statistic minus the hypothesized parameter over the standard error, but not this standard error. Different. It's going to be pH QH over N, which is, let me go ahead and put this up here. On the top, we're going to have 0.522 minus 0.5 over the square root of 0.5 times 0.5. Well, my marker's not working very well. That should be 0.5, 0.5, that's just nothing, divided by 500. So this 0.5 is the 0.5 from your hypothesis. So again, it's kind of like with the two proportion z-test. We're assuming HO is true. And if HO is true, then our best estimate of P is the 0.5 from the null hypothesis, and that's what we use when we calculate standard error. No hypothesis, we don't have that, so the best estimate is the 0.522 from our sample, the 261 divided by 500. And I just finally checked. I was right. It's 0.522. In this one, if you were using the p-value, again, I'm not going to, we are about out of time here. P hat, the middle of this is going to be the 0.5. We're going to have the 0.5. I don't know why it's doing that. 0.522 is right here. And the p-value is here. It's going to be in one-tailed, only the upper tail, because we just have a one-tailed test. Sample size large enough? Yes, because 261 yeses, 500 minus that, 239 no's. Both of those are greater than 10, so your sample size will be large enough. I'm not going to say a lot about number 8 because I think we've already done one like this, but just to remind us, we have a sample standard deviation of 16. it's going to be a t-test because we have sample standard deviation. And there's only one sample of 50, and there's your mean. So we have x bar is equal to 74, n is equal to 50, standard deviation is equal to 16, standard error, I'm not writing the formula out now, but it's going to be 16 divided by the square root of 50. Our research hypothesis or alternative hypothesis is going to be mu less than 77. And when we draw our sampling distribution, it's going to have an x bar on it. The center is going to be mu equal to 77. And we had a sample mean of 74. And since this is less than, that shouldn't be less than or equal, I was just circling that to be less than before that messes somebody up. Our p-value is down here because that's the direction we're going. So if mu is equal to 77, there's a, whatever the p-value comes out to be, chance of observing x bar less than or equal to 74.